13.3, part 2. So I think it's interesting. It's exciting now learning about partial derivatives, because what happens in math and in physics kind of mirrors, because the physics, you need the math to do the physics. What we do is kind of a process of refining. So we do one thing, and then we add a little more detail. So for example, when you first study physics, you motion, it's all algebra. You do it algebra based, and then you do a little bit of calculus, taking derivatives and that kind of thing, and then you refine a little more, and you work on understanding things based on a little more complicated math, which most of us did with projectile motion under a little bit of duress. And then you add some more complications, and it's not just taking integrals and derivatives. You solve differential equations, but then you add more detail, and things can vary in position and in time, with position and in time, and you come to partial derivatives. And then the things that are describing the physical stuff are partial derivatives and partial differential equations. So when you see it a little bit, if you study electromagnetism in physics, if you're taking physics, and electromagnetism is all about partial derivatives. All the Maxwell's equations are all partial derivatives. And interestingly, in terms of partial differential equations, the example that popped into my head when I was thinking about this stuff this morning is so Schrodinger's equation, which is a partial differential equation which describes elementary particles, electrons, protons, that kind of thing. If you solve that partial differential equation, Schrodinger's equation, in spherical coordinates for example, an electron, what you get out of that is the shapes of the orbitals that you learn about in chemistry. So all these orbital to sp whatevers, those things that are kind of ad hoc stuff that they say this is how it works. Well, it actually comes from solving a partial differential equation that gives you the shape and the structure of those orbitals. So it's an interesting thing. Comes from solving partial differential equations. All right, so what we're going to do today is we talked about taking a partial derivative. We want to take higher order partial derivatives. We want to take second partial derivatives and third partial derivatives, etc. So we'll give the example with a two-variable function. Z equals f of x, y. For second derivatives, we have four possibilities. So our first possibility is we can take the derivative with respect to x and then take the derivative with respect to x again. And we can write that f sub xx. And this is the same as so this is our subscript notation. With differential notation, we're taking the derivative with respect to x of the derivative with respect to x. And we write that d squared f dx squared.
Are those d's, or are they
These are the curvy d's. We're talking about partial derivatives. So we take the partial derivative of f with respect to x, and then we take the partial derivative with respect to x again. So that's notated either f sub xx or d squared f dx squared. We could take the partial with respect to x and then take the partial with respect to y, because the partial with respect to x is still a two-variable function. We're going to write that f sub xy. And that's going to be the partial with respect to y in differential notation of the partial of f with respect to x. And we write that d squared f dy dx. Now notice in the subscript notation and in the differential notation, they're in opposite orders. Because here, subscript notation, we're going from inside out. Here, with differential notation, we're going from left to right. So we're taking the derivative with respect to y of the derivative with respect to x. So pay attention to that in the notation. For the order, it tells you to take the derivatives in. We could start, our third possibility, we could start by taking the partial with respect to y, and then take the partial with respect to y again. So that's f sub yy. So that's going to be the partial with respect to y of partial f with respect to y. And that'll be d squared y, f dy squared. And then finally, our fourth possibility, we can take the partial with respect to y, and then take the partial with respect to x. So that's f sub yx. That's the partial with respect to x of the partial with respect to y. And then our notation there would be d squared f dx dy. And again, note on these partials, for the subscript notation and the differential notation, the order is reversed. And I'm going to put a little star here. Number 2 and number 4, we call the mixed partials.
Nice, Kevin. Partial. You're a genius, Kevin.
And if we're talking about function of more than two variables, we could talk about the second mixed partials and the third mixed partials and the fourth mixed partials, etc. So if you have a 3-variable function, you have a lot of possibilities, more possibilities for a third partial. And if you have a 4-variable function, you have more possibilities for the fourth partial.
And the test, you're going to give us one like that? Like, X, Y, Z, W, like,
No, I think the most, for the most part, the most we'll ever do is three variables.
Fine.
If you go further in calculus, in advanced calculus, you can prove that if these mixed partials, if our partials are continuous, if our functions are nice, then the mixed partials are equal. And we're going to rely on that fact for a lot of things. So we're just going to say, I'm just going to state that as a fact. So for f of x, y, with our mixed partials continuous, and we're talking about it continuous in some region of the plane, then our mixed partials f sub xy equals f sub yx in that same region. So in general, we're going to say the mixed partials are equal. And this holds for a function with 3 or more variables. If the function is nice, then the third mixed partials are equal. For a 3-variable function, the third mixed partials are equal. For a 4-variable function, the fourth mixed partials are equal. So this is true as we generalize to more variables. Yes.
So why does it matter what order you do them?
For a second partial, it doesn't.
Okay.
But the reason we need to know this is sometimes what will happen is we'll do some operation, and what we end up with is 2 different mixed partials, and we realize that they're the mixed partials of the same function. So then we can say, oh, these are equal, and that'll let us simplify things. So usually we use it in the other direction. We recognize that those are second mixed partials of a function, therefore they're equal, and then we can simplify our calculations.
Oh, so they're not going to look the same necessarily, or because why were you saying like earlier? You said make sure you know the order of which one they're in. I thought you were saying something like that.
So if we were doing, for example, if we were doing a third partial derivative, and we started with, if we started with, in this process, if we had say we have a 4 variable function and we're doing let me go backwards. We have a 3 variable function and we want the second mixed partials of that 3 variable function. We need to make sure we go in the correct order to get those second mixed partials. Because with a 3 variable function, it's the third mixed partials that are equal, not the second mixed partials. So it's just to pay attention to the order that you're doing a derivative in, or in general with a multivariable function. All right. So the process of taking mixed partial derivatives, not complicated. It's just we're repeating what we did last time. So I want to go through one example where, let's say, the problem says z equals x to the 4th minus 3x squared y squared plus y to the 4th, and we want to show that f sub xy equals f sub yx. So we want to demonstrate for this particular function, we've been told in general that that's true, but we want to demonstrate that for this function. So that just means we need to take the mixed partials and see if they're equal. It could turn, this is a polynomial, so we know it behaves nicely. If we have some other strange function, we might end up with a function that's not necessarily continuous, and maybe our mixed partials would not be equal. This one should be. All right, let's take some derivatives. The partial with respect to x. You get 3x to the 3rd minus 6x y squared. 4, thank you. I was combining integration and derivatives somehow. And the partial of z with respect to y is, when we take our partial with respect to y, what do we get? Minus 6x squared y plus 4y to the 3rd. Is that right?
Yeah.
Okay, I did it correctly. All right, so then we'll take the partial of this with respect to y. Partial with respect to y of dz dx. And we get minus 12xy. And we take the partial with respect to x of dz dy. And we get minus 12xy.
So, Mr. Beamer, what do the partials tell us about the function?
So the partials would tell us,
Like the xy tells about the function.
so that would tell the rate of change of the first partial with respect to y. So if we think about those surfaces we looked at yesterday, where we had the function and we graphed the partial derivatives, so that would be the slopes of those surfaces in the x direction and in the y direction.
So it doesn't tell us about concavity.
We will use second derivatives. So for concavity, we're going to test for a maximum, minimum, or a saddle point. We'll have a second partials test.
But so that only works when you have fx and x and fy and y. It doesn't work when you mix the variables up.
Well, the second partial test will involve xx, yy, and xy.
And presumably YX.
Well, we can, the xy and the yx are interchangeable. So, but we have a few more things to do before we start talking about those things. All right, good. Are we good there? All right, let's look at another one. Let's look at a 3-variable function. F of x, y, z is x squared minus 3xy plus 4yz plus z cubed. Relatively simple 3-variable function. And we want to show, let's show that the third mixed partials are equal. Fx, yy, fyxy, and fyyx are equal. Just how the problem is stated.
So would all of those also be equivalent to the terms with z in them, or is it only consistent within each 2-variable set?
No, so all the third mixed partials would be equal.
Regardless of which 2 variables.
Right,
or
which
3 variables
right,
we're using.
which variables we're using. So we just pick 3 of them instead of all 6 of them?
Yeah,
Yeah,
9 of them.
9? Is it 9?
Yeah, because you can do the same
Right.
set.
All right, show that these are equal. All right, so let's take some derivatives. Partial with respect to x of this thing. What do we get? 2x minus 3y. Partial with respect to y. Minus 3x plus 4z. And the partial with respect, we don't need the partial with respect to z. F sub, let's see, what do we need? F sub yy is 0. What's F sub xx?
2.
We don't need xx, okay?
So we use x, y.
F sub xy, negative 3. Do we need any others? Yx, F sub yx is negative 3. And when we take the derivative of any of these, is this xx?
No,
Can't read
that's
my,
y.
this was yx?
That should be y.
Okay. When we take the derivative of any of these with respect to the other variable, what do we get? 0. I'm going to say all equals 0. And all the other mixed partials that involve the z terms would turn out to be 0 as well. So with the mixed partials, there's really not a lot new. Yes?
I don't think every single triple partial is equal. Because f of z, z, z.
That's not it.
That's
Sorry.
not a mix.
It's not that.
Oh, it's not mixed?
That's a pure.
Yeah, the mixed partials are, the third mixed partials are equal. So if we're mixing the variables in some way. All right, so then there's not a lot new. Yes?
It would be equal no matter how many you did, as long as they're mixed.
Yes, as long as they're mixed. And then whatever combination of the 3.
So you could just like f of x, y, 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 y would equal f of
There has to be 3.
Right.
Y, X, X, Y,
Yeah.
2Z.
yeah. As long as it's the
There has to
same.
be
Right,
3.
right, right. All right, so again, not much new here. I have a few questions that I want to ask the class, kind of thinking about what these partial derivatives are telling us. And then we'll be done. We'll work on our activity. And I want to, before we go on, I want to kind of introduce a topic that we're going to talk about tomorrow with what we call differentials. I want to talk about differentiability a little bit. All right, so here are my questions for you. Let's let n equal the number of applicants to a university. Let's let P equal the charge for food and housing. And let's let T equal the tuition.
Take it back.
All right, so can we agree that n is some function of P and T? The number of applicants to a university is somehow related. Some
Accepted applicants?
no, just applicants.
So like never a lot of applicants, that's a high tuition.
So they're saying that we're can we agree that the number of applicants somehow depends on how much it costs to go to the university?
Sure.
Yeah.
If you're not going to be able to afford to go, you're probably not going to apply.
That's not true.
All right.
Ever heard of the FAFSA?
Yeah, I'm very well acquainted with the FAFSA.
Oh, good.
And on the other side of the FAFSA, not the front side, the back side, where money starts going the other way.
Oh.
Yes.
Oh, taxes.
Oh.
What's that?
Taxes.
Thank you for your first charity.
Not taxes. It's when the money comes out of my account to pay back what FAFSA gave me. Yeah.
Wait, what?
Yeah, you have to pay back. You have to pay back student loans. They're kind of picky about that.
It's not free money. I just spent it all.
Yeah. That's why when you get that check, you don't go out and buy stuff. You actually pay for school.
Wait, I
This
know
is
once
why
you
we
turn
can't have
18,
real
you
world
just get a
examples.
plastic card that just
Buys
gives
and stuff, right?
Like,
Yeah. Just get unlimited stuff.
10 years later, you get a bill and it's like,
This is US, baby. Debt isn't real.
Maybe one let me take it.
All right, so we're agreeing that this n is a function of p and t, and this function is such that the partial of n with respect to p and the partial of n with respect to t are both less than 0. What does this tell us?
Oh, as the price for food and housing increases, the number of applicants decreases.
Right, as the price for food and housing decreases or increases, the number of applicants.
And then same for tuition.
As the cost goes up, as costs go up, the number of applicants go down.
More dollar,
supply curve. Quantity of supply versus price.
I don't know.
All right, these next ones are true or false.
Well, money, let's see.
False. Nobody wants to make the comment.
True.
Number one, I'm going to say if z is an f of x y, function of x and y, and the partial of z, write it this way, partial of z with respect to x equals the partial of z with respect to y, then z
What are those squiggles?
And.
and sorry, I forgot. I printed the two letters and I wrote the and in cursive.
That was pretty great.
I'm so sorry.
Someone's gonna mysteriously.
So we're going to say this is a function where the partial of z with respect to x equals a partial of z with respect to y. So we're saying, well, if that's the case, then z is some constant times x plus y. Is this true or false? So what we're looking for is, if it's false, let's write a function where the partial of z with respect to x and the partial of z with respect to y are the same, but z is not the constant times x plus y.
I'm gonna go with true.
I'm going true.
I'm going false. I don't know the example. but
False.
there's gotta be
There's
False.
nothing. I'm
There's
going
gotta be
true.
something.
It's false. There's a sign. We did this as a homework. Sine of 3x plus 3y.
Well, the derivative with respect to x would be would have a cosine.
Yeah, they're both would be.
3x plus 3y.
Yeah.
Oh,
They
yeah.
both would be the same.
Okay. So what is it?
By
Z equals
sine of 3x plus 3y. Dylan.
sine of 3x plus 3y.
Yes.
Right. So the partial of z with respect to x
Isn't
is
that just the same thing? Sine just
The fact that it has a
Sine is
This is just, it's just you're doing something special to x plus y.
Except the c would be 0. 0 times x plus y.
Oh yeah, I forgot. Sine is a constant.
Yeah, sine is a constant.
3 cosine. Is it 3 cosine?
Hey, it's sine is small.
Yes, sine
Sine is small.
Classic.
Its sine is 3 constants. S, I, and N.
Oh, nice.
Yes.
Or as I.
And dz dy is the same.
It's just negative s squared n squared.
Wow. I'm right again. Those are all.
The one that I thought of, was z equals x plus y plus 1.
Oh, that works.
Or z equals e to the x plus y. That one works, right?
The easiest.
Etc. So this is false.
Dylan. Giving you pride of accomplishment.
Second one, true or false? Z equals f of x times g of y. So this multivariable function is some function of x times some function of y. So, I don't know, sine of x times cosine of y, something like that. Then, partial of z with respect to x plus the partial of z with respect to y equals f prime x times g of x plus f of x. This should be y, sorry. F of x, g prime of y.
Surely that that's not acceptable.
gotta be.
Airplane joke.
Well, let's take some derivatives.
Let's derivify.
What's the partial of z with respect to x?
Don't mind if I derivative.
Isn't the partial of g with respect to x f prime of x times g of y? G of y is a constant because that's just a function of y. And dz dy, f of x is just a constant. Right?
So you just do like normal.
Right. Well, this is f of x is a constant with respect to y. G of y is a constant with respect to x.
True.
So this is true.
Ballsy.
So interestingly, when you solve partial differential equations,
It's true. That's why it's
you look for solutions that are products of the individual variables because it makes things nice and simple. Why do you do it that way? Well, because it just turns out nice. In the partial differential equations course I took as a graduate student, it said, we're not going to explain why these things are true. We're just going to say this is how we find the solution. I said, that sounds like engineering, not math.
Boom.
All right.
Mic drop.
If z equals e to the xy,
Wait, is it true false?
This is true, false. Yes. This is number 3. Sorry.
How many do we have?
I think this is the last one. Then we'll talk about differentiability.
So you just went false, true, so we gotta be false again.
Or that's what they'll think you'll
Then
Oh, but then that's what I think you'll think, so it's gonna be false. That's your argument. That was
Then this mixed partial is xy plus 1 times e to the xy. Yeah, take a derivative and see if it's true. Derivative. Oh yeah, I'll pretend I didn't hear that.
Derivatate. For Caucasian.
Hold on. Wait a minute.
That's based on what?
dy over dx.
What's dz dx? Y e to the xy. And then
Chain rule with
d dy of dz dx is product rule. First time the derivative of the second
XY.
plus the second times the derivative of the first.
Wow, that's not cool.
And then we can factor this, right? We can make it look nice.
Oh, it's close.
It's the big.
Oh. So that's true.
Oh, yeah.
All right, so I want to introduce a topic that we're going to talk about tomorrow when we talk about differentials, differentiability.
How many lines are we?
This many.
A whole room. You're not gonna fit it in your entire notebook.
Good luck.
I should start learning about what the way you do it.
Oh, were those your drawings on there, Lily? No, they were Calc 3 drawings for sure.
Yeah, no, we draw.
No, sometimes I just need like an extra oh, we visualize this. I'm gonna draw Helix instead of on the desk. I erased it.
At home and in here I have a desk pad that's just blank paper. That's I move stuff aside and I have to draw something. All right, differentiability. So for a single variable function, we say that f of x.
Wait, how many lines do I need for this?
Not a lot. Not a lot. Half a page maybe.
Oh, alright.
Because we're going to draw a picture too.
Apple's kids page, which is like not that much.
So for a single variable function, we say that our function is differentiable if this limit as h approaches 0 of f of x plus h minus f of x over h exists. And for a single variable function, we said that differentiability implies continuity. So if a function is differentiable, then it's continuous. So there's a nice relationship between differentiability and continuity. Now continuity does not apply differentiability because you could have an absolute value function that's continuous, but at the vertex it's not differentiable. All right, I want to look at this function. F of xy. Very simple two-variable function. Equals 0 if x times y is not 0, and equals 1 if x, y does equal 0. So let's draw a picture.
Wait,
You got stupid gamer.
Oh, I said not, but I forgot to put my...
Okay.
No, it's the other way around.
Oh my god.
This
Trying to be
guy.
back here.
Hey.
That's like those problems that you get. Make this a true statement by moving one matchstick. Then just move the matchstick from the.
That's a thing.
Yeah, I mean, you see that? It's like they make an equation with a matchstick and they say, make this not true by moving one matchstick. Or make it true moving.
Because you could just like remove one
All right, so what is this function going to look like? Let's draw this. It equals 1 where x times y equals 0. Where is that? When x or y equals 0? So where x or y equals 0?
On the x-side.
So above the x-axis or the y-axis, this thing's going to equal 1. So we're going to get a line like so above the x-axis and a line like so above the y-axis. So that's where it equals 1. And where x, y is not equal to 0 is everywhere else. So that's going to be down here on the, where's my, no, not the palette, I want a blue highlighter. There we go, okay. So down here on the plane is the rest of the function. All right, so let's look at the limit as x, y approaches 0, 0 of f. Along y equals x, what is the limit? So along this, it would be 0, right? As we get closer and closer, our limit is 0. Along y equals 0 or x equals 0, what's our limit? 1. So our function at 0, 0 is not continuous. And in fact, it's not going to be continuous along the axes. But, so our function is not continuous at 0, 0. What is the slope? What is f sub x or f sub y along here? Partial with respect to x, partial with respect to y equals 0. What is the partial of x or partial with respect to y down here? Also 0. Therefore, f sub x or f sub y equals 0 everywhere. So here we have a function where the derivative exists where it's not continuous. So for multivariable functions, we get this strange thing happening where the derivative can exist at a point of discontinuity or an infinite number of points of discontinuity. So just saying this limit exists is not enough to define differentiability, because we don't want to define differentiability in such a way that our function is differentiable where it's not continuous. We want it to be more consistent with our idea of function that we developed from single variable calculus. Yes?
So if function's equal to 1 only at one single line, how can you tell the derivative with respect to something perpendicular to that line? Or do you just go back to the equations? Like just like since you have one line, how can you tell the rate of change perpendicular to that line?
So the rate of change of the function perpendicular to that line would be, so at that point,
Yeah.
at a point on this line, the rate of change with respect to y, we're not going uphill or downhill at all, so it would still be 0. So for multivariable function, we need some other definition. We need a different definition of differentiability. And we'll talk about that definition next time. So I wanted to introduce why we need a different definition with a relatively simple function.
One 24-hour commercial. Be right back.
All right. Homework.
You don't leave us on a cliffhanger? I'm never been so invested in math.
And I'm just going to back up here just to take care of Michael's little quibble. And I'm going to say f of x or f of y equals 0 at 0, 0. So our derivative is equal to 0 at that point. So our function is, the derivative exists at that point, but it's not continuous at that point. Okay, homework. Page 896 again.
All right.